Hi, this is Mr. Miller and welcome to another video. This one is on SI units and prefixes. Let's get going. Okay, so the standard units in the SI system. SI is the international system, or Système International. Pardon my French, I know it's not very good. So the first unit that we use is the one that goes along with the dimension of length, which is the meter. Originally, the meter was intended to be 1/10,000,000th of the distance from the Earth's equator to the North Pole at sea level. Its definition has been refined to reflect the growing knowledge of metrology, which is the science of measurement. Since 1983, it has been defined as the length of the path traveled by light in vacuum during the time interval of 1/292,792,458ths of a second. Okay, that's not a real long time. It's basically how far light travels in a second. Okay, the next unit that we use is the unit that goes along with the dimension of mass, the kilogram. The gram was originally defined in 1795 as the mass of 1 cubic centimeter of water at a temperature of 4 degrees Celsius, which makes the kilogram equal to the mass of 1 liter of water. The prototype kilogram, manufactured in 1799 and from which the current kilogram is based, has a mass equal to 1/25,000,000th of a liter of water. The kilogram is the only SI base unit with an SI prefix, kilo, with a symbol of K as part of its name. It's also the only SI unit that is still directly defined by an artifact rather than the fundamental physical property that can be reproduced in different laboratories around the world. 4 of the 7 other base units in the SI system are defined relative to the kilogram, so stability is really important. You actually bring your nation's prototype copy to France, to Paris, and compare it to the prototype that's kept in ideal environmental conditions at the offices in Paris. Okay, so the next unit that we're going to look at is for the dimension time, which is the second. Between 81,000 and 1960, the second was defined as 1/86,400th of a mean solar day. That definition still applies in some astronomical and legal uses. But between 1960 and 1967, the second was defined in terms of the period of the Earth's orbit around the Sun, taken in the year 1900. But it's now defined more precisely in atomic terms. Seconds may be measured using mechanical, electrical, or atomic clocks. Astronomical observations in the 19th and 20th centuries revealed that the mean solar day is slowly but measurably lengthening in time and is no longer considered a suitable basis for definition. With the advent of atomic clocks, it became feasible to determine the second based upon fundamental properties of nature, and since 1967, the second has been defined to be 9,192,631,770 periods of the radiation corresponding to the transition between the 2 hyperfine levels of the ground state of cesium-133 atom. In other words, the oscillation, 9 billion oscillations of that radioactive cesium atom. The final unit that we use a lot in physics is for electrical current, for the dimension that goes along with electrical current. It's called the ampere, named after Andre Ampere. It's commonly called the amp. It represents that constant current which if maintained in two straight parallel conductors, think wires, of infinite length, of negligible circular cross-section, so think very long, very small wire placed 1 meter apart in a vacuum, that would produce between these conductors a force equal to 2 times 10 to the negative 7 newtons per meter of length of the wire. Now there's some other units that we need to know about that we don't necessarily use in physics. I know you've used this one in chemistry. It's the amount of a substance called the mole. We don't really deal with that too much in physics. Maybe for the GT students, when we get to dealing with the number of electrons in amount of matter, or in E&M when we do the same, but not so much. The next one is the luminous intensity. We really don't use that in our study of physics. It's the candela. It's how much light is radiant on a certain region of space. And then temperature. The unit is the Kelvin, and that's named after Lord Kelvin. We'll use it, but only when we're trying to account for how materials change as their temperature changes. Usually we use that in electricity. Now, why are we so concerned about these units? Well, in 1999, there was a mission to Mars that failed, and 24 hours before this mission's orbital insertions, calculations placed the orbiter at an altitude of 110 kilometers, and 80 kilometers considered to be the minimum altitude that this mission, the Mars Climate Orbiter, was thought to be capable of surviving during the maneuver. Final calculations placed the spacecraft in a trajectory that would have taken the orbiter within 57 kilometers of the surface of Mars, where the spacecraft likely disintegrated because of atmospheric stresses. The primary cause of the discrepancy was an engineering error. Specifically, the flight system software on the Mars Climate Orbiter was written to take thrust instructions using metric unit newtons. That's the unit for force in the SI system, and we'll be using that, while the software on the ground that generated those instructions used the imperial measure of pounds, which are the unit of force that we're familiar with when we tell somebody how much we weigh. This error has since been known as the metric mix-up and has been carefully avoided in all missions since then by NASA. Hopefully we don't have any of those metric mix-ups in our class. Now, any other unit besides these 7 Saturn units is considered a derived unit. There are some units that we use that aren't proper scientific notation, however we're allowed to use them, and there are units such as the radian, the degree, a meter squared, that sort of thing. Now here's a question to see if you were paying attention. So which of the SI units is the only one still defined by a physical artifact? Go ahead and answer that on the Google form that goes along with this video. Feel free to pause or rewind while you do that. Welcome back. Now we're going to talk about SI prefixes. Now, we use those prefixes as a way of displaying larger or smaller units without needing to use scientific notation. For example, some of the units that you might see are kilograms, kilometers, milliseconds, megagrams, centimeters, or microseconds. So, here's a table that shows the name of the prefix, the symbol for the prefix, and its scientific notation, base, and exponent. So if you were to see a kilo with a meter, you would replace the kilo with times 10 to the 3 meters. Or a microsecond, you replace that symbol for micro, the mu, with times 10 to the minus 6th. And that will tell you how many of that base unit you have. Where it gets a little bit difficult is when you're working with kilograms. Let's say you have a nanogram. That represents 10 to the minus 9th grams, but our standard unit is a kilogram. So you have to figure out how many grams you have, and then you make the conversion up to kilograms. Now, to see if you've got this all figured out, I have another question for you. Be sure to answer on the Google form that goes with this video. Well, have a great day, and we'll see you in class.